The purpose of today's experiment is to measure the velocity of projection of this ball when it is projected horizontally from a spring-loaded gun. Now, this experiment has two parts. In the first part, we will investigate the relation between the horizontal range of this projectile and the vertical height from which it is projected. Well, in the second part, we will use the conservation of momentum and the conservation of energy to investigate the velocity of projection. So it's a combination of projectile motion and the conservation of momentum and energy. A very good experiment. In the first part of the experiment, you will project this ball from a vertical height. Now, that is the vertical height of the ball from the level of the table to where the ball is. That is the vertical height. We project the ball from a vertical height we call Y0, and then measure the horizontal range. Now, watch when I project this ball. You need to watch the trajectory and also watch where it is falling so that you can measure the horizontal range. Alright, watch it. You need to mark the position where the ball fell on the table and measure the distance between where the ball fell and the position. Now, I have marked the initial position of the ball. That is where it is. And I will keep an object down here when you are ready for measurement. So your measurement will be from the initial position of the ball to where the ball fell, and that is your horizontal range X. So let's say the ball is now projected with a velocity V0 from a height which we call Y0. And the ball falls at a distance X, which is the horizontal range. Okay, I don't think you can see that Y0. The Y0 is the height from which the ball is projected. Alright, now how are these two related? Suppose the time taken by the ball to fall on the table is t. Now tell me, during that time t, what happens to this V0? V0 will not change because there is no force pulling or pushing the ball in the horizontal direction. Therefore, we can say the horizontal range X equal to V0 times t. And during that same time t, the ball is also falling vertically through a height Y0. Can you tell me what that Y0 equal to in terms of this t and the acceleration due to gravity? Of course, the initial vertical velocity of the projectile is 0. Therefore, Y0 equal to 1/2 gt squared. So x equal to V0t and Y0 equal to 1/2 gt squared. Y0 and x both are covered at the same time t. That means if you can eliminate the t between these two equations, we can write a relation between Y0 and x. Alright, I want you to take a couple of minutes and do that now. Alright, have you written the relation between those two? Well, all we need to do is solve for t from here. What is t equal to? T equal to x divided by V0. And take that t into here, and let me write it over here. You have y0 equal to 1/2 of gt squared, and I'm going to replace t by x divided by V0. So t squared will be x squared divided by V0 squared. Is that right? So that will be x squared divided by V0 squared. We have eliminated time. That means we have now an equation in terms of two variables. What are our variables? Y0 is one variable, x is the other variable. Now in the experiment, I will be asking you to change Y0. You can see I will fire this ball from different heights, and I will ask you to measure that h. Alright? Now, that means your independent variable is h, and your dependent variable, well, it is not h, we call it Y0. Your independent variable is Y0, and your dependent variable is x, the horizontal range. That means we need to solve for the dependent variable x. Is that right? Alright, let's solve for x. I can say x squared equal to, what is x squared equal to? Can you solve for x squared? Now, 2 and V0 squared are on the denominator, so that will be 2 V0 squared times Y0. That will be 2 V0 squared times or divided by G times. So it will be 2 V0 squared divided by G multiplied by Y0. Now check if that equation is right. You're supposed to write it on your own. Now we have an equation in the form y equal to mx. Is that right? Now this is the dependent variable and this is the independent variable. If you therefore draw a graph of x squared on the y-axis and y0 on the x-axis, the slope of that graph will be 2 V0 squared divided by G. And we know the value of G, therefore we can obtain a value of V0. That is the first part. Alright. Now in this experiment, you need to measure distances. What are the distances that you need to measure? You need to measure the distance y0 and also the distance x. That means we now need to work out a conversion factor. Let's start by working out the conversion factor. What I would like you to do is, I have a 30 centimeter ruler placed against this background. Now use your protractor or your divider or compass to measure the distance of this ruler on your computer screen. Alright? Record it as the measured length. Then what will be your conversion factor? Your conversion factor will be, you are familiar with it, let me write that anyway. The conversion factor will be equal to 30 centimeter divided by, that is the actual length of the ruler, divided by your measured length on the computer screen. So 30 centimeter divided by the measured length. This is your conversion factor. We'll call it little c. That means any measurement that you do from now on the computer screen for this part of the experiment, Remember, this conversion factor is valid only for this part of the experiment. For the next part, we will have another conversion factor. So for all the measurements that you do for this part of the experiment will be multiplied by this conversion factor. Okay, so do that conversion factor. If you haven't got it done, I have the ruler here once again. Do that now. I'm going to give you about 20 seconds. Measure the length of that ruler on your computer screen and work out the conversion factor C. Are you ready for taking measurements? Let's start with the first Y0 value. The first Y0 value, measure the height from the tabletop to the center of the ball. In other words, use on your screen, use your divider, see, like this, and measure the distance between the tabletop and the center of the ball. That is your first Y0. Alright, and I'm going to fire the ball, and you need to locate where the ball falls exactly and measure the distance. Now, where is the distance measured from? The distance will be measured, look at the mark on the equipment. It is going to be measured from that position to where the ball falls. So if the ball falls here, then your X will be that distance. Alright, so you need to observe very carefully and see where the ball is going to fall. Alright, watch this. Have you located the position? If you located the moment you locate the position, you can pause the video and then measure that distance. Alright, I'm going to give you 2 more trials. For each Y0, I will give you 3 trials, and you need to measure that distance X for 3 trials and then take the average. Alright, let's do the second trial. Alright, watch carefully the second trial for the first Y0. Let's go. I'm going to fire it. Watch it. Now I'm going to do the third trial for the first Y0. Watch it again. I have now increased the height Y0, and you need to measure it. Measure it from the tabletop to the center of the ball. You see? Measure it from the tabletop to the center of the ball. That is your second Y0. Alright, measure that now and multiply it with the conversion factor C. And that is your second Y0. Alright, once you are ready, we will now do 3 trials for the X value. Okay. Ready for the first X value? Now remember, X value will be measured. What is the point on the table from where you will take the measurement? Directly below the ball. So for the X value, you will measure it at a point directly below the ball to where the ball falls. Alright, I'm going to do the first trial for X. Okay, there goes. There you are. Now, if you notice, the ball fell actually there. So, your distance will be measured from directly below the ball to where it fell. This is your distance X now, where I'm pointing. From here to here is your X. Okay? Measure that and multiply it with the conversion factor. Alright, ready for the second trial? Alright, I'm going to fire it and watch carefully where it falls. I will give you a few seconds to mark that position and measure that distance. Always remember, you need more time. Pause the video and then take your own time, but take the measurements very accurately. Alright, I'm now going to do the third trial for the second Y0. Alright, watch again carefully. I have now increased Y0 to a third value, and I want you to measure that Y0. But before you measure it, let me load the ball in. There you are. So measure the distance from the center of the ball to the tabletop. That is your new Y0. Okay? Measure that and multiply it with the conversion factor. And ready for the first trial for X value. Alright, watch carefully. The first trial for X value. There goes. Alright. Okay, take your time and measure that distance X. And now we are ready for the second trial. Okay, I'm waiting for you to finish the first reading. It really doesn't take a long time. Okay, the second trial for X. Mark that distance. Watch carefully. And now the third trial. Okay, ready? Let's go over the third trial. Watch carefully. Watch it. I'm going to fire it now. Measure that distance and find the average of the three X values, and that is the horizontal range for this third Y0 value. I have now increased the height to a fourth Y0 value. Measure that height from the tabletop to the center of the ball. Alright, measure that height and multiply it with the conversion factor C. This is your fourth Y0. Okay? Ready for the first trial on that fourth Y0? Okay, I'm going to fire. I'm going to give you this time some warning. I'm going to say ready, 1, 2, 3, go. I hope you marked that position and measured that X value. Alright, I'm going to give you 10 more seconds. Let's now do the second trial for X for the fourth Y0 value. There goes. Ready? 1, 2, 3, go. Alright, you mark the position and measure the distance. We will now do the third trial for the X value for that Y0. Ready? 1, 2, 3. 3, go. Alright, have you measured the length? You got 3 x values and find the average value for that y0. I have now increased y0. You now need to measure the new y0. Measure the height from the tabletop to the center of the ball. That is the 5th y0. Alright, and I hope you remember the x value is measured from a point directly below that ball. Say from that point and on to where the ball falls. Okay, are you ready for the first trial for the 5th y0 value? Or you want a couple more seconds to measure that height? There we go. Measure the height y0, the 5th y0. Okay, let's do the first trial for x value there. Ready? 1, 2, 3, go. Have you measured the value? Alright, let's now do the second trial on that y0. Ready? 1, 2, 3, go. Mark that position and measure that distance. We will now do the third trial on that y0. Okay, let's go. Ready? 1, 2, 3, go. Mark that position, measure that x, and now find the average of those 3 x values. I have now changed y0 to a new value. This is the 6th value. So measure that y0 from the tabletop to the center of the ball. Alright, the 6th y0, measure that on your computer screen and multiply by the conversion factor. Okay, ready for the first trial for x there? Let's go. Ready? 1, 2, 3, go. I hope you located the position and measured the x value. We will now do a second trial on that 6th y0 value. Are you ready? Alright, ready? 1, 2, 3, go. Locate that position and measure that distance x. Are you now ready for the third trial? Alright, ready? 1, 2, 3, go. Locate the position and measure the value of x. You have now 6 different values of y0 and the corresponding values of x, and draw a graph of x squared on the y-axis and y0 on the x-axis. Measure its slope and use the value of the slope to calculate v0, the horizontal velocity of projection. Well, that is the first method. We will now look at the second method. In the second part of the experiment, we will use the same mass. The mass of this ball we will represent by lowercase m, and its value is 63.8 gram. You will need that mass, so make a note of that. We will use the same ball and we will use the same spring-loaded gun. So that means the velocity V0 will remain the same. Is that right? So the same gun is used and the same ball is used, making sure that V0, the velocity of projection, will not change. Our aim is to measure the velocity of projection V0. Now, what we will do is, we will fire this ball into a pendulum assembly. The mass of the pendulum assembly is represented by the uppercase M, and it is 116 gram. Alright? We will fire this ball into the pendulum assembly and watch what happens when I fire the ball into the pendulum assembly. There you are. Now, the ball and the pendulum collided perfectly inelastically and the system moved away. Now, I want you to understand these terms. V0 is the velocity when you fire the ball. That means the moment when the ball hits the pendulum, its velocity will be V0. When the ball gets lodged into the pendulum, the system, at the instant when the collision occurs, the system moves away with a certain velocity. And we will represent that velocity by V sub f. So understand these terms. V0 is the initial velocity of the ball before the collision. Vf is the velocity of the ball and the pendulum just after the collision, at the instant of collision. That means with that velocity, the system will climb to a height h. So the system, that means the system means the pendulum plus the ball. The pendulum plus the ball has kinetic energy just at the instant when the collision occurs. And all that kinetic energy gets converted to potential energy when it climbs to a height h. That means we are now going to measure the height to which the system is raised. Now that is the measurement that you need to do in this part. How do you measure that height? Alright, to begin with, you need to measure the height of this ball from the top of the surface of the gun assembly, where I'm pointing. Alright, measure the distance from the top of the, what do you want to call it, the platform to the center of the ball. Now, in order to do that, we need once again a conversion factor. So let's work out the conversion factor. I have once again arranged that 30 centimeter ruler. I want you to measure the height of this ruler on your screen. Alright, measure that height, and then 30 centimeter divided by the measured height is your conversion factor. So obtain that conversion factor. Alright, measure this height on your computer screen, then divide the actual length, which is 30 centimeter, by your measured value, and that is your conversion factor. Now record the conversion factor C. So write down the conversion factor C. And now, what is the theory of this part of the experiment? As I have told you, we are going to use the conservation of momentum and the conservation of energy. Now, first of all, what is the total initial momentum Pi? What does initial mean? Before collision. Now, before collision, only the ball has velocity. The pendulum has no velocity. That means all the momentum is the momentum of the ball. The ball has a velocity v0, it has a mass m, so Pi is the initial momentum before collision, that is m times v0. Now what is Pf, the final momentum? The final momentum is after the collision. The mass of the system is the mass of the pendulum plus the mass of the ball, and the velocity of the system just after collision is v sub f. Therefore, Pf, the final momentum, is the total mass small m plus big M times Vf. Now, according to the conservation of momentum, the initial momentum must be equal to the final momentum, and that gives us one equation: mv0 equal to m plus m Vf. Alright, let's leave that equation there and now consider the conservation of energy. Now, what is the initial energy? Again, the initial kinetic energy we now look for. We are now not interested in the ball before it is fired. We are going to look at the conservation of energy for the pendulum assembly. The pendulum assembly has an initial kinetic energy. What is the kinetic energy of the pendulum assembly immediately after the ball gets lodged? The velocity is Vf. Therefore, the kinetic energy will be 1/2 mass is small m plus big M times Vf squared. That is the kinetic energy of the system the instant when the collision occurs. And all that kinetic energy now becomes potential energy. If the ball is raised through a height h, the potential energy of the system will be this: m plus big M times gh. So all the initial kinetic energy becomes potential energy. So this is the conservation of energy equation, and this is the conservation of momentum equation. Alright. In the second equation, in the energy equation, if you notice, m plus m will cancel on either side, and we can solve for Vf squared. Multiply both sides by 2. What do we get? We get Vf squared equal to 2gh. And therefore, what is Vf equal to? Vf is square root of 2gh. So, I'm going to write that over here. We've got Vf equal to square root of 2gh. If you now take this value of Vf over to the momentum equation, let's do that. We will say m times v0 equal to small m plus big M times Vf, and Vf is going to be replaced by square root of 2gh. There you are. Now, that is the equation that connects V0 to everything else. Can you solve for V0 from here? What is V0 equal to? V0 equal to small m plus big M over small m, that quantity times square root of 2gh. Now, you know the values of small m and big M. We will measure the value of h, and that way you can calculate v0, the velocity of projection. Okay, now in that case, we will do 5 trials. We will measure the h value for 5 trials, and you find the average value of h and use it in this equation to find v0. Okay? If you are ready, let's do the measurement. The first measurement you need to do is the initial height of the ball. You need to measure the height from the surface of the equipment to the center of the ball. That is your initial height. Let's call it h0. Okay? Now measure that and multiply it with the conversion factor. And now I'm going to fire the ball, and you need to measure the height to which the ball is raised. Alright, watch how the ball is going to be raised. There goes. You now need to measure this height. The height from the center from the top of the equipment to the center of the ball, and that will be h1. So you have h0 and h1, and calculate your h as, let me write it here, h equal to h1 minus h0. That is your height the ball is raised. Okay, now this is the first trial. I'm going to give you some time for you to measure that height. Alright, measure the height from the surface top to the center of the ball. That is your h1. Okay. Let's now do a second trial. h0 is always the same, so one measurement is enough. Alright, let's do a second trial. Watch it carefully. There goes. Alright, measure the height of the ball from the top of the equipment. Multiply that with the conversion factor and calculate h as h equal to h1 minus h0. That is your second trial. Ready for the third trial? Let's go. Measure the height h1 and calculate h equal to h1 minus h0. Now we have the fourth trial. Ready? Let's go. Measure that height h1 and calculate h equal to h1 minus h0. Let's now do the fifth trial. Alright, ready? Go. Measure that h1. You have now 5 values of h, and find the average of that h and use that average value to calculate v0. You have now measured v0 using 2 methods, and now find the percent difference between the 2 values. Now let me take you quickly through a couple of questions at the end. Well, once you have the value of v0, you can use that to calculate the value of Vf. If you remember, This one, mv0 equal to m plus mvf. That is the momentum equation. So using the value of v0, you can calculate vf. That is the velocity of the pendulum ball system immediately at the instant of collision. You know your m, you know your big M, and calculate your vf. And then I have asked you to calculate the initial kinetic energy and the final kinetic energy and the kinetic energy lost during collision. You see, when this ball, which had an initial kinetic energy, what is the initial kinetic energy, which you call, say, EI or KI? Now, that is the kinetic energy of the ball. That is 1/2 mv0 squared. And after the collision, the kinetic energy of the system is your EF, and that will be 1/2 of m plus big M vf squared. So calculate the initial kinetic energy and the final kinetic energy and obtain the percent energy lost. You know how to do that. And now the third question. You know that momentum can be expressed in the kinetic energy can be expressed in terms of momentum. If you remember this equation, we did that in the theory. Kinetic energy can be expressed using the linear momentum k equal to p squared over 2m. So let's apply this for this collision. Well, what is the initial kinetic energy? This time I'm going to use Ki for initial kinetic energy. The initial kinetic energy can be written as Pi squared divided by 2m, where Pi is the initial momentum. And the final kinetic energy, Kf, can be written as Pf squared over 2 times the total mass is the mass of the ball plus the mass of the pendulum. Alright? You can now use these two equations to establish a relation between initial kinetic energy and the final kinetic energy. Now tell me, if I divide Ki by Kf, or let's divide Kf, find the value of Kf divided by Ki. What's that equal to? Kf is this value, Pf squared divided by 2 times m plus m. Divide that by Ki. Well, dividing is the same as reversing and multiplying. So that will be 2m divided by Pi squared. Well, you know that initial momentum equal to the final momentum. That means Pi squared equal to Pf squared. So those two will cancel. And the 2 also will cancel. So we got Kf over Ki is small m divided by small m plus big M, or Kf can be written as small m over small m plus big M times Ki. The final kinetic energy given in terms of the initial kinetic energy. Therefore, what is Ki minus Kf? The kinetic energy lost. So that will be Ki minus Kf. I'm going to use this quantity. That will be m over m plus m over Ki. Now, in the third question, I have asked you for the fractional kinetic energy lost. What's the meaning of fractional kinetic energy lost? It is the energy lost divided by the original energy. So if you divide the energy lost by the original energy, this is the fractional energy lost. So divide the right hand side by Ki. Can you simplify that and tell me what that is equal to? You know here, on the numerator, Ki and Ki will factor out and cancel with this Ki. That will leave you with this quantity, namely 1 minus m over m plus m. So this is the fractional energy lost. I want you to simplify it and make it into a good looking expression. In fact, you can answer the third question from here. Okay, I think this has been a good lab, and I want you to do one thing. This lab is going to be used as an assessment lab. In other words, we want to find out how well you have actually mastered the techniques and skills that we want you to master in a course like this. Now, have you mastered the skills of writing a good report? Have you mastered the skills of critically evaluating your measured values? Have you mastered the skills of interpreting the data, using the slope and calculating a given value? Have you mastered the skill of criticizing the accuracy of measurements? You see that? So all these we are going to assess. Now remember, this is not for your grade, this is for our own purpose. So I want you to submit 2 copies of this lab. 1 copy just with your ID only, no name, because that copy is not for grading you. And the second copy is the normal copy that will be used for grading. Alright? So send me 2 copies of this lab in order that we may use 1 for the assessment and 1 for the normal grading. Okay, I will see you for the next lab later on.